Okay, so example 4 from lecture 10 is to find the electric field intensity everywhere due to an infinite sheet of charge. Now we already derived this in the previous lecture, but now we want to derive it using Gauss's law. So previously we used Coulomb's law to derive it. Now we're going to use Gauss's law to prove that what we derived earlier was the same, and to exercise the use of Gauss's law. So let's say that the infinite sheet of charge is in the x, y plane, okay? So here's the x, or the z-axis, the x-axis, and the y-axis, right? So here's x, here's y, here's z, okay? So what do? Remember, when we use Gauss's law, the first thing we should do is always write down Gauss's law. Gauss's law says that the net outward flux is going to be equal to the charge enclosed. And this is for a surface which is called our Gaussian surface, right? So we have to select a Gaussian surface. We want to select a Gaussian surface that is either perpendicular or tangential to the normal vector of the or the normal vector of the surface is either perpendicular or tangential to the field. Now remember, we have to have some intuition about what the field is going to look like in order to do this. And we do. We already worked through problems in Coulomb's law, and we know that the field is going to be directed in the z direction above the plane and in the negative z direction below the plane. Okay? So if we pick a Gaussian surface, which is a box, that's going to work perfectly because the top and the bottom are going to have surface differential surfaces which are normal to the field lines, and the sides of the box are going to be perpendicular to the field lines. So we'll get no flux passing around the sides of the box and flux passing through the top and the bottom. So selecting a box that passes through the plane. So where I draw this dotted line here, it's cutting right through the plane. Okay, and then we'd have on the other below the plane here. Okay, so the box is basically containing some section of the plane, and we want to find out what the charge enclosed in that little section is, and then set it equal to the net outward flux. So I'll draw the field lines in red. So we know based on our intuition that the field lines are going to be directed this way above the plane and this way below the plane. So we can clearly see that when we do this flux integral, we don't have to worry about any of the sides because there is no flux passing through them, because the field lines are tangential to the surface on the other side. So all we got to worry about is the top and the bottom. Well, let's think about this. What is ds on the bottom and what is ds on the top? So first I'll say ds on the top, and I'm going to say that ds on the top is going to be equal to, obviously, change in the x direction, change in the y direction, and the vector that's normal to it is obviously going to be in the az direction. Okay? That's pretty easy to see. And then likewise, if we look at the bottom, right, the bottom part of the sphere here, and let me just draw this to show it a little bit better. So we have, right, so we want to find out what the normal is on the bottom. Well, we can see that it's going to be the same as the top. The only difference is it's going to have a different direction, which is going to be obviously in the negative az direction. So now we can integrate this. Let's look at the left-hand side, right? So we're going to have, for the top, let's say we start at some x point. Why don't we just put it in the xy plane and go from 0 to some width we'll call w, right? Because we can just pick arbitrary points. And then we can go from 0 to some length in the y direction, right? And then we want to find out what is so what is d? Well, on the top, it's going to be equal to dx dy, right? And it's only going to have a z component, as we showed right there, right? It's only be directed in the z direction. So this right here is the top. Okay? Now, whenever we look at the bottom, we should note that the bottom, the component of the flux, is also directed in the negative az direction, right? So when we add the bottom, we'll say, again, the dimensions are going to be the same for dx and dy. However, dz is going to be negative dz because it's directed in the negative z direction, and then we'll have that multiplied by negative dx dy, because you can see that the differential surface vector is in the negative az direction. So whenever we multiply those two out, we just get a positive there. So you can see here we're going to have L times W times dz, and here we're also going to have L times W times dz. Okay? So multiplying that out, we get 2 times L times W times dz. Okay? And that's the left-hand side of Gauss's law, which is the net outward flux. Now, let's find out what is the charge that's enclosed in that little space right there that we is enclosed by the Gaussian surface. Okay? So for the charge enclosed, what we have to do is add up all the little differential charge particles in there. Well, we can say that each one of them is equal to the surface charge density, right, times the area, right, and that differential area would be dx times dy. And what's the dimensions? Again, going to be the same dimensions, 0 to L, 0 to W, or sorry, I should say 0 to W, and then 0 to L. Okay, and when we do this, we get length times width times rho sub s. Okay, so the next step is then to simply set the left-hand side equal to the right-hand side. And doing that, I have 2 length width times dz is equal to length width times rho sub s. And from here we can see that L and W simply cancel out, as we did expect that to happen. And then we can say dz is simply equal to rho sub s divided by 2. So you can see this confirms what we derived easier, that as long as we have an infinite sheet, it doesn't matter how far we are away, we see the same flux. It's only dependent on what that normal direction is. So from here we can say that E is going to be equal to rho sub s divided by 2 epsilon naught, and then it's going to be in the A normal direction. Okay? So what is the A normal direction? Well, it depends on what side of the plane we're on. If we're above here, the normal direction will be going up this way. If we're below the plane, it would be going this way. So this is the exact same result when we use Coulomb's law to derive it.